So recall that we are in the middle of Toda's theorem, which says that polynomial hierarchy can be computed using sharp set. So for that we defined this parity P class, and we showed that SAT can be reduced to unique set and hence parity set. This is the Valiant-Vazirani lemma, which actually used hash functions. Okay, so the satisfying assignments, they are hashed to buckets, and the bucket 0 will with high probability have a unique satisfying assignment. That's the idea. And yeah, so NP has reduced to parity P, and now we will convert NP to the NP. So this reduction is, you can think of it as NP reducing to sharp set, which is not very interesting, but unique set is interesting. And the interesting thing will be that this parity will now be used as a quantifier itself. Okay, we will replace there exists for all with this single parity quantification. So lemma 1 will be about parity quantifier. So let psi be a Boolean formula on top of which you have C there exist for all alternating quantifiers. So we'll convert psi into a formula A r comma psi, which will be in parity set with high probability if psi was true, otherwise with low probability. Okay, this will be both sided errors. So let's do the proof sketch. So the idea is replace the for all there exist quantifiers one by one by the parity quantifier. And do induction. So let's induct on Boolean formula psi, which has let's say parity on top 0 1 to the L. So string z in 0 1 to the L space, and let me remove this part. So first there is a parity quantifier, then there is a there exists quantifier, then there is a for all quantifier, and the formula is phi zxw. Right, so 3 strings differently quantified. We'll convert this there exists to parity, and then for all also to parity. In fact, all 3 into single parity quantification. Now let me write down the domain. So this domain is 0 1 to the L. This is 0 1 to the N, and this is 0 1 to the K. So now by the Valiant-Vazirani technique, we can get a formula tau such that for random string r, the probability over R. So now parity, so basically what will convert is Villian-Vazirani will convert the there exists quantifier into parity, right? So there exists X will become parity X, and then there will be for all W phi and tau XR is true with high probability. So this is the part. This tau x comma r is the part which it comes from the hash function when you express it as a Boolean formula in Villian-Vazirani proof, right? And so this happens if there exists X for all W, phi is true. If that part of the formula is true, then actually there exists can be replaced by unique X, and hence we can replace it by parity X. Essentially there is a single X which will satisfy this. Moreover, this probability will be 0 if it is false. And or while probability over R parity X for all W phi and tau XR so this is true. This probability is 0 if that formula was false. Right, that is the full Villian-Vazirani result, that true with high probability and false with certainty when the formula is true, respectively when the formula is false. So which means that now on top of this event or this expression, what happens when you add the parity Z quantifier? So when you add the parity Z quantifier for a single Z, the probability is 1 by A10. So if there are 2 raised to L Zs, so the probability will be worse. Okay, so that is what you get. So probability over R for parity Z and this expression all you can say is this is greater than or equal to 1 by A10 to the 2 raised to L. If the formula psi which was parity Z, there exists X for all W phi sorry, this is Z parity Z, there exists X for all W psi is equal to true. So if psi is true, then this modified formula with parity on X, although there is some positive probability, but it's very small. It's not as big as 1 by A10 because Z is coming from 0, 1 to the L space. So for every z you have to ensure that this transformation is correct, and that happens with multiplicative probability. So although we have reduced this randomly reduces psi to parity zx for all w, phi and tau, but the success probability is very low. Okay, so this is not satisfactory because we cannot call this a efficient reduction, randomized reduction, unless the probability is good. Actually, in the lemma, we want the probability to be 2/3. So in this step, the success probability should be very high, something like a constant 2/3. So how do we increase this probability? That's our current question. So how do we increase this probability from 1/18 to the 2 to the L to 2/3, right? That is the question. So the thing we have to do is somehow for every z we will significantly increase the success probability from 1/18 to almost close to 1. So that will be the idea. So for a fixed z, bring the probability, let's bring the probability close to 1. Let's implement this. So for a fixed z, instead of just one random string or one experiment R, you do T experiments, okay, and take an OR. If any one of those experiments is true, then we are good. Okay, so do these many experiments and take an OR. So for a fixed z, repeat the transformation. T times for random strings R1 to RT. So what happens? So we are looking at probability over R1 to RT, or for all these and so now Velin Vazirani for many RIs. So basically this tau I is tau x comma RI. Okay, so run this for various random strings R1 to RT and then take an OR over all these checks. Okay, and whether this OR is true, that's what you are checking, whether this OR is equal to true. So what is this probability now? So this is see this event is 1 minus the event that all of them are false, right? But what is the probability of being false? That is 1 minus 1 by A10, and that t times. Okay, that error has to be repeated t times, so the probability of error is 1 minus 1 by A10 to the t subtracted from 1. Okay, so if you take t very large, then this probability is very close to 1, because a fraction raised to t kind of becomes 0. So this probability becomes kind of 1. Of course, assuming that the original formula was true, if there exists x for all w phi is true, else the probability of the same thing probability of this expression being true when the formula was false, that is 0. That is not 0, that is the error case, right? So that's 1 minus 1 by A10 is the error t times. Okay, for the false case, something being true, see the original formula was false, but one of these experiments comes out to be true. This probability here, in case the formula was false, right, then all these instances of Valiant-Vazirani that you do for R1 to RT, they will remain false no matter how many times you repeat them. So the OR will also be false. So chance of that becoming 0 is actually of it becoming true is actually 0. Okay, so that's the key observation, that in multiple experiments, going from a true formula to all t of them false, that probability is very low. And going from false, coming from false, going to these t being false, that probability is 1. So that's what we achieve. So this is called probability amplification. Okay, the success probability has been amplified, the error probability has been brought closer to 0. Now let us consider the z's. So this we did for a fixed z. Now let's keep changing z, go in the space 0, 1 to the L. So then the probability, again R1 to RT, parity z, I1 to T, one of these is true. Right, this whole thing equal to true. So what is this probability? See, assuming that to begin with psi was true, let's assume that psi is true. So in that case, this parity z, OR operator, parity x, Valiant-Vazirani, what is the chance that all of them is, each of these is false? Let us just compute that probability. So these are T experiments. The error probability of one experiment is 1 minus 1 by A10. And so 1 minus 1 by A10 is the error probability for one experiment. You do it T times, so error is times T. Moreover, look at these Z's, right, which were making psi true. So the number of these Z's is 2 raised to L. Okay, so that also we have to take into account by union bound. So that is the union bound acting. So again, going over all these good Z's and for each these T experiments, the error probability is upper bounded by 1 minus 1 by A10 to the T times 2 raised to L. So the success probability is inverse of that, 1 minus that. Okay, so this is what we want to make sure is high. And what happens otherwise? So if psi is false, then what happens is when you consider this probability, so this is the error probability. In the false case, this experiment giving you true, that's an error. So when will that happen? See, if you again go over these Z's, which were, since the formula was false, psi was false, it means that the number of Z's where you get true is even. So you go over those, and in those cases, one of these T experiments giving you true, if you calculate that probability, you will get upper bound 2 raised to L times 1 minus 1 by A10 to the T. Okay, so the error probability will be this much. So basically consider the Z's when the inner formula is true and when it is false. So what happens with the false case? The false case will remain false. What happens in the true case? The true case giving you true, right? That or the true case giving you false, that probability is 1 minus 1 by A10, and from that you can calculate this upper bound. So let us now analyze this for T. So now you take T to be quite large, 16 NL. So that will give you that 2 raised to L times 1 minus 1 by A10 to the T. As T increases, again this expression should tend to 0, right? That's the rough intuition. So you will get, you have to estimate this, A10 times 2L, that's 16 NL. So 1 minus 1 by A10 to the n for large enough n is at like 1 by E. So you get 2 raised to, in fact it's less than equal to e raised 1 by e raised to 2l. Right, e is around 2.78, so this is definitely less than 1/3. Okay, so this error part is less than 1/3. So in the true case, you get 2/3 success, and the same thing when size falls, you get error to be 1/3, success to be 2/3. So which means that we have randomly reduced psi to psi prime. So what is psi prime? Psi prime is parity z I1 to t experiments, t instances of Valiant Vazirani. Inside is parity x for all w phi and tau x comma ri. Right, and so this thing we can call phi I zx. Okay, this depends on zx and ri, so we are calling it phi I z comma x. The only thing which is extra is the OR operator. Right, we have almost reduced it to single parity quantification, but we also have to now remove this OR. So we now remove the OR operator. So how do we do that? So let's consider a simplified OR, which is OR of two expressions with parity x. A simplified situation. So parity x f1x or parity x parity y f2y. So now here we will show the idea of removing this OR. Okay, it's OR of parity operators. So how do we convert this into a single parity operator or single parity quantification? So this will be a bit tricky. We will introduce some new variables and try to modify this f1 f2 and actually then take AND of the modification. So always remember that this first part is saying that either f1 has odd number of assignments or satisfying assignments, or f2 has odd number of satisfying assignments, one of these, right? So it's also possible that first has odd, the second has even. So it might make sense to let's do the following. So introduce new variables u1, u2, u3. And a +1 operation on formulas. So what will this +1 operation be? This is as follows. For formula fx, define f plus 1 as it will be two cases. U equal to 0 will be just f, or you may set u to be 1 and fix x to be 0. Okay, that is the +1 operation. What it is doing is it's just growing the number of satisfying assignments by 1. So let's write this down. It grows the number of satisfying assignments by 1. That is, if you look at the number of satisfying assignments of f plus 1, then you get the original thing plus 1. Okay, so number of satisfying assignments has grown exactly by 1. Now, how does this thing help? So if you started with f1 even, it becomes odd. And if f2 was also even, it becomes odd. So you can multiply the two, so you get odd, and again add a +1, so that is even. Okay, so even can be mapped to even this way. Any other combinations like even odd even, or odd, they will all go to odd. So let's write that down. So going back to what we had before, parity x f1 or parity y f2, define parity of x, y, u1, u2, u3, and use +1 3 times. So you have f1 plus 1 formula, f2 plus 1 formula, take a conjunction of those two, and then do a +1. Okay, so this is in x u1. This is in x u2. And this whole thing is then in it's not x u2, this is y u2. And this will add u3. So you will have x, y, u1, u2, u3. Okay, so 3 variables have been added, new variables. And you can see that in case f1, f2 both have even number of, or say, so when is this formula false? Right? It is false when the number of solutions, satisfying assignment should be even. So even would mean that this product F1 plus 1 and F2 plus 1 is, yes, how many times is it that counting you have to do. So let me write down. So this is true if and only if parity X F1 or the other one parity Y F2 is true. Only when F1 and F1 or F2 have odd number of satisfying assignments, then only in that case you will get odd here. If both of them have even, then this product will be odd and odd plus 1 will be even. Okay. So this you can easily prove. So it just follows from this: odd times odd plus 1 is even, while anything else you do even times odd, even times anything, anything you put here will be odd. Just use this property. Okay, odd times odd plus 1 is even, any other combination plus 1 is odd. So that gives us a powerful tool, and now we'll use it.